Hello everyone, I'm András Retzler and I'm going to talk about the ReSMILE technique, which is a method for system identification for linear parameter varying systems, and it allows us to trade off model accuracy and complexity. So I'm excited to share our results with you, and among other things, I'm going to talk about how to identify a linear parameter varying model for an overhead crane like this one on the right. So, we've been working on this project with my colleagues at KU Leuven and Budapest University of Technology and Economics. And what is the ReSMILE? It stands for Regularized State Space Model Interpolation of Local Estimates, and it has been described in the paper of Dora Turk. The original SMILE technique without regularization comes from the work of Jan de Kényi. Now let's start with linear parameter varying systems. A linear parameter varying or LPV model of a nonlinear system is typically used when the system shows linear behavior while a parameter of it is fixed. This parameter is called the scheduling parameter. It's possible to have LPV models with multiple scheduling parameters as well, but here we are considering a single one. Let's take the mentioned overhead crane as an example. The input to the system is the velocity of the cart and the output is the position of the load. However, the system only behaves linearly when the cable length is fixed. So what we can do is that we make the cable length our scheduling parameter, and we identify LTI models of the system, in this case state space models, at different cable lengths. Let's group our state space matrices into a single matrix P. Here are our local LTI models corresponding to different values of the scheduling parameter. Now we want to be able to tell the state space matrices for the scheduling parameter values in between, what we can do by interpolation. We interpolate by B-spline fitting. Those are the data points, and that is the spline. As a result, we get one B-spline per each element of the P matrix. This set of splines allows us to tell the state space matrices at any given scheduling parameter value, so it can be considered as an LPV model of the system. Anyway, we created this model to design a controller for it later. An LPV controller measures the scheduling parameter in real time and updates the controller dynamics accordingly. The Linear Control Toolbox, also known as LC Toolbox, is an open source MATLAB toolbox that was developed at our MECO research team in order to bring LPV control design to industrial application. In our work presented here, the LC toolbox has been extended with the ReSMILE technique to provide LPV identification functionality. In addition to creating an LPV model by interpolation as shown before, the ReSMILE can also simplify the model to make sure that it's feasible to design an LPV controller for it. To understand how does that work, we need to talk about B-splines first. A B-spline is a function which gives a curve like this. To calculate a B-spline, we need to give a set of knots that we see here as blue dots. Actually, the knots define the basis functions as shown here in different colors. The basis functions are piecewise polynomials. The spline itself is the weighted sum of these basis functions. So in the end, to define a spline, we need the knots, the coefficients for the weighting, and also a spline degree, which was not mentioned yet. It is the order of the polynomials of the basis functions. And as a note, due to the recursive formula used, we need to include the first and the last knot in the knot sequence multiple times, based on the spline degree. To give an intuition on these concepts, here is an animation on how a spline is changing while its coefficients are changing. So what are the advantages of using B-splines? Local support makes identification robust against outliers, and the positivity of basis functions allows for relaxations of linear matrix inequality constraints during control design. Back to the ReSMILE. Assuming that we have our spline interpolated model, if it has many knots, the LPV controller synthesis could take a very long time. By removing some of the knots from the splines, we can make them much faster. We have to make sure, however, that the error between the input data and our simplified model is as small as possible. This is an overview of the ReSMILE processing steps, which will also show how this problem is solved. In the first step, state space models are transformed to the same basis, allowing to interpolate them with splines. At this point, we might have too many knots, so the next step is to figure out which knots can be removed by solving an optimization problem in a loop. The accuracy versus complexity can be controlled by different parameters, but in general, if more knots remain in the end, that means higher accuracy. In this step, we solve a second-order cone problem using Casadi's OptiSpline interface and the Mosaic solver. We calculate an importance value for each knot, which tells about their contribution to the spline. We attempt to push those values down using regularization and to increase the sparsity of the solution by using reweighting. And in the last step, we remove the knots whose importance is below a given threshold, ending up with the simplified LPV model. Our contributions include an open source implementation of the ReSMILE available on GitHub. This code is also integrated with the LC toolbox. We provide different datasets for testing and also the corresponding example code. Let's take a look at the output of the ReSMILE for the crane dataset. So you can see the knot importances on the slide from the second knot to the last but one. In this case, all the knots, except from the first and the last one, can be removed because their importance turns out to be lower than the default threshold. Now let's take a look at the resulting splines. Each graph corresponds to one element of the P matrix combined from the state space matrices. The green dashed line is the final result. The red dots correspond to the input data. The green dashed line fit the red dots with only a small error. Note that the blue line is an internal result and it doesn't affect the final result. The code to generate this output is shown here. It's just a few lines. So then there's this other example dataset, which is based on random generated splines. This is again the diagram of the knot importances for this dataset. Here we see that the algorithm removes 26 out of 30 knots. The green dashed line is on the red dots nicely here as well, which means that the simplified spline fits well the input data. We also have a simple UI that gives an insight into how the algorithm operates internally. We can plot different things like spline coefficients or how different variables change over the iterations. It also allows us to plot the frequency response function of the resulting model. This is the amplitude characteristics of the LPV model of the crane. As you see, it's basically made from both plots. Frequency on the x-axis, magnitude on the y, and the third dimension is the scheduling parameter. This other one is the phase characteristics. An improvement we have made to the algorithm is detecting splines that appear as straight lines based on the variance of their derivatives. For those, we add additional constraints during the simplification step. We also suggested default values for the parameters of the algorithm. These worked well with our example datasets. The initial knot distribution is still an open problem, but it can be explored using the toolbox, which provides several choices on that. Putting the knots on the scheduling parameter values corresponding to the input models worked well. To summarize, our open source implementation of the ReSMILE allows us to create a spline-based LPV model from a set of LTI state space matrices corresponding to different scheduling parameter values of the system, in a format that is compatible with the Linear Control Toolbox control design routines. The complexity of the model can be reduced on the expense of accuracy. Thank you very much for your attention. Here are the URLs on the right for you to find the code if you are interested. And if you have any questions, let us know. That's all for now. Have a nice day and goodbye.